Greetings, and thank you for tuning in. We will briefly introduce our paper VisionThink in this video. Let me begin with the main achievement of our VisionThink. VisionThink significantly outperforms previous state-of-the-art, efficient vision language models, including FastV, sparse VLM and VisionZip, across multiple benchmarks. Unlike traditional efficient VLMs that rely on a predefined token compression ratio, VisionThink dynamically decides whether to compress visual tokens based on each image question pair. This smart strategy enables our model to excel especially on strong OCR-related benchmarks. Furthermore, while prior attempts to apply reinforcement learning in vision language modeling have been limited to narrow tasks like visual math, they fall short on general visual question answering, due to the limitations of rule-based evaluation. To overcome this, we introduce a LLM as judge strategy that enables RL to generalize beyond visual math. Another key contribution is the efficiency gain. By smartly deciding when high-resolution input is needed, VisionThink can reduce inference time without sacrificing accuracy. For example, on DocVQA, VisionThink achieves nearly 3 times speedup with less than 1% accuracy drop. On MME, it even improves performance while having inference cost. Let's now dive into the motivation behind our approach. We observe that on weak OCR-related benchmarks, even compressing the image to 1/4 size does not lead to significant performance degradation. This indicates that most real-world images contain a large amount of redundant visual information. However, on strong OCR-related benchmarks, performance drops sharply when compressing images, suggesting that high-resolution details are critical for accurate understanding in such cases. This raises a key question. Can we make the model smart enough to decide whether it needs a high-resolution image? To address this, we propose VisionThink. In most real-world cases, we first resize the image to 1/4 size, then input the question and compressed image into the model. If the model can confidently answer the question, this saves 75% of the visual tokens. But if the low-resolution image is insufficient, the model outputs a special token requesting a high-resolution image, which is then fed into a second inference round. This branch incurs only 25% additional token cost, and is triggered only when necessary. To effectively train the model on general VQA tasks, we first analyze the limitations of traditional rule-based evaluators. As shown in the figure, while the ground truth answer is 47, valid predictions can vary in expression, such as those shown in predictions 1 through 4, making it difficult to judge correctness using matching rules. Therefore, we use a LLM as judge strategy to perform answer evaluation purely based on text, ensuring more accurate and flexible judgment in general VQA scenarios. To train VisionThink via reinforcement learning, we carefully design a reward function, accuracy reward, based on LLM judgment of correctness. Format reward ensures output matches expected structure. Penalty reward discourages overuse of high-resolution requests and encourages learning when it's necessary. More details are shown in the paper. For experiments, we build on Qwen 2.5, VL, 7B and evaluate VisionThink across multiple benchmarks. Results show that VisionThink matches or surpasses the baseline model, achieving notable gains on MMVet and MME, even outperforming many closed-source models. To validate our LLM as judge RL pipeline, we scale the training data to 130K examples and observe significant gains. Furthermore, VisionThink also accelerates real-world inference time, especially for reasoning VLM, while maintaining performance on both general and OCR-heavy benchmarks. Compared to prior efficient VLMs, VisionThink achieves better performance using fewer visual tokens, particularly on strong OCR benchmarks like ChartQA. Moreover, the model smartly decides when to use high-resolution images. On strong OCR tasks, the high-resolution request ratio exceeds 60%. On weak OCR tasks, it stays low. Lastly, we provide several discussions in the paper. We explain why we adopt reinforcement learning over supervised fine-tuning. Why we do not introduce a cold start stage. How different system prompts affect model behavior. And how VisionThink differs from traditional efficient VLMs, while also exploring the potential for integration. In summary, we propose VisionThink, a method that enables the model to smartly decide whether high-resolution input is necessary, significantly reducing inference time while improving performance. VisionThink achieves significant good results on OCR-related tasks, and with the LLM as judge strategy, we extend RL beyond the narrow domain of visual math to the broader landscape of general VQA. Thank you for your listening. All code and models will be released.